Today we are going to talk about the multiplication of rational numbers. So the product of two rational numbers p by q and r by s can be defined as p into r by q into s. Let's take an example of two values 2 by 7 and minus 3 by 8. The product of these two numbers can be obtained by multiplying the numerators and denominators together, which means 2 into minus 3 upon 7 into 8, which gives us minus 3 by 28. Please note that I forgot to mention a minus sign before 3 by 8. Similarly, if we multiply minus 3 and 4 by minus 5, we get minus 3 into 4 divided by 1 into 5, which gives us 12 by 5 or 2 by 5. A quick point to note before we move on is that when a rational number is multiplied to 0, the product will always be 0. Now let's look at properties of multiplication of rational numbers. The first one being the closure property. Closure property states that if p by q and r by s are two rational numbers, then p by q into r by s is also a rational number. Let's understand this through an example. If we multiply minus 2 by 3 and 5 by 7, we get minus 10 by 21, which is also a rational number. Next up is the commutative property of multiplication of two rational numbers. So if p by q and r by s are two rational numbers, then p by q into r by s is equal to r by s into p by q. Let's understand this through a very quick example of minus 4 by 7 and minus 8 by 5. In order to verify the commutative property, we will multiply both the values in two different orders and check whether the resulting product in both the orders is the same. So the first one is minus 4 by 7 into minus 8 by 5, which gives us minus 32 by 35. Similarly, we also calculate minus 8 by 5 into minus 4 by 7, which again gives us the value of minus 32 by 35. Thus, we have verified that the multiplication of two rational numbers is commutative in nature. Next up is the associative property of multiplication of two rational numbers, which states that if p by q, r by s, and t by u are three rational numbers, then p by q into r by s into t by u is equal to p by q into r by s into t by u. Let's understand this using an example of minus 2 by 3, 3 by 5, and minus 5 by 6. In order to verify the associative property, we need to first solve it in the order minus 2 by 3 into 3 by 5 into minus 5 by 6, where we will evaluate minus 3 by 5 into minus 5 by 6 first, and then finally multiply minus 2 by 3 to it. Our final value comes out to be 1 by 3 as shown here. Next, we will evaluate minus 2 by 3 into 3 by 5 into 5 by 6 by evaluating minus 2 by 3 into 3 by 5 first, and then multiply minus 5 by 6 to the final product. This gives us the final value of 1 by 3 for this order as well, thus verifying the associative property of multiplication of rational numbers. Following the associative property, let's try to understand the multiplicative identities. So for every rational number p by q, there exists a rational number 1 such that p by q into 1 is equal to p by q. Therefore, the number 1 is called the multiplicative identity of a rational number. Let's take the example of minus 2 by 3. So if we multiply 1 to it, we will again get the value of minus 2 by 3. And that's how we verify the multiplicative identity of 1. This again builds up to the multiplicative inverse or the reciprocal of a rational number. So for every non-zero rational number p by q, there exists a rational number q by p such that p by q into q by p is equal to 1. Thus, q by p is the multiplicative inverse or the reciprocal of p by q, and p by q is the multiplicative inverse or the reciprocal of q by p. Some special points to note. Firstly, 0 has no reciprocal. And second, the reciprocal of 1 is 1 and minus 1 is minus 1. Let's understand this concept through a very quick example of 7 by minus 3. So if we multiply minus 3 by 7 to it, we will get the answer of 1. Thus proving that the multiplicative inverse or reciprocal of 7 by minus 3 is minus 3 by 7. Now let's understand the distributive property of multiplication over various operations. The first one being over addition. So if p by q, r by s, and t by u are three rational numbers, then p by q into whole bracket r by s plus t by u is equal to p by q into r by s plus p by q into t by u. So in essence, we are just opening the bracket and multiplying p by q to both the values. So the example below will make everything a lot easier. So we have three values, minus 3 by 4, 2 by 3, and minus 5 by 6. We will first solve the left hand side, which is minus 3 by 4 into whole bracket 2 by 3 plus minus 5 by 6. Here we will first simplify the expression within the bracket and then multiply minus 3 by 4 to it. And it gives us the final value of 1 by 8. Next, we will solve the right hand side, which is minus 3 by 4 into 2 by 3 plus minus 3 by 4 into minus 5 by 6. We will solve both of these expressions simultaneously as there is no precedence one over the other. And finally, this is simplified to get 1 by 8. And as we can see, the left hand side is equal to right hand side, thus verifying the distributive property over multiplication. Now we will look at the distributive property over subtraction of multiplication, which states that if p by q R by S, and T by U are three rational numbers, then P by Q into R by S minus T by U is equal to P by Q into R by S minus P by Q into T by U. Let's verify this through an example. We have three numbers minus 2 by 3, 4 by 5, and 7 by 11. We will first solve the left hand side of the equation, which is minus 2 by 3 into whole bracket 4 by 5 minus 7 by 11. And here we will evaluate the expression within the brackets first, which is 4 by 5 minus 7 by 11. And then we will multiply minus 2 by 3 to it. This gives us the final value of minus 6 by 55. Next we will solve the right hand side, which is minus 2 by 3 into 4 by 5 minus 2 by 3 into 7 by 11. As none of the expressions have a precedence, we will solve them simultaneously. This gives us the simplified answer of minus 6 by 55. As we have proved, the left-hand value is equal to the right-hand value. We have verified that the distributive property of multiplication over subtraction exists. We will now look at the division of rational numbers. It states that if P by Q and R by S are two rational numbers, then P by Q divided by R by S is equal to P by Q into S by R, which is equal to P into S divided by Q into R. Let's understand this through the example of 4 by 9 and minus 5 by 9. So we get 4 by 9 into 9 by minus 5, which can be simplified as 4 into 9 divided by 9 into minus 5, which gives us the final value of minus 4 by 5. Similarly, if we divide 2, 3 by 7 by minus 4, we get minus 17 by 28. Some points to note. Divisibility of a rational number by 0 is not defined. That is, P by Q divided by 0 does not exist. And second, 0 divided by any non-zero rational number will always result in 0. Let's look at the properties of division of rational numbers. First one is the closure property. If P by Q and R by S are two rational numbers which are non-zero, then P by Q divided by R by S is also a rational number. Let's verify this through an example of minus 2 by 5 and 3 by 7, which gives us minus 2 into 7 divided by 5 into 3, which is equal to minus 14 by 15. Is this a rational number? Yes. Next, we need to understand that division is not commutative in nature. And this means that if P by Q and R by S are two rational numbers, then P by Q divided by R by S is not equal to R by S divided by P by Q. Let's again take the example of minus 2 by 5 and 3 by 7, for which we already calculated the value as minus 14 by 15. And now let's calculate 3 by 7 divided by minus 2 by 5, which comes out to be 3 into 5 divided by 7 into minus 2, which is equal to 15 divided by minus 14. As these two values are not the same, we verify that the commutative property under division does not hold. Now let's look at the associative property of division. If P by Q, R by S, and T by U are three non-zero rational numbers, then P by Q divided by R by S divided by T by U is not equal to P by Q divided by R by S divided by T by U. Let's understand this through the example of minus 7 by 6, 5 by 8, and minus 2 by 11. First, we will evaluate the left-hand side of minus 7 by 6 divided by 5 by 8 divided by minus 2 by 11, which gives us the final value of 56 by 165. Next, we will evaluate the right-hand side, which is minus 7 by 6 divided by 5 by 8 whole divided by minus 2 by 11. And this gives us the final value of 154 by 60, which is not equal to the left-hand side. Therefore, we verify that under division, the associative property does not hold. So now we come to the final section of our chapter on rational numbers, and this is representing rational numbers on the number line. So in the 7th class, you've already learned the process of representing rational numbers on a number line, and let us now review it. So in order to represent the rational number on a number line, we proceed as follows. So we first draw a straight line and mark the arrows on both sides of the line to show that the line is continuously indefinite in both directions. Then we mark the point on it and label it as O, and that represents 0. Then we select a unit length and mark points on the line at unit length intervals from each other on both sides of 0. And then we label these points on the right hand side of it as 1, 2, 3, and on the left hand side of 0 as minus 1, minus 2, and minus 3, and so on. Let's try and represent different rational numbers on the number line. First, we'll try 1 by 2 and minus 1 by 2. So we will first divide the line segment between 0 and 1 into two equal parts, and the point that represents the middle is point 1 by 2. And now we divide the line segment between minus 1 and 0 and divide it into two equal parts, and that point in between is minus 1 by 2. And that's how it represents these two numbers on the number line. Similarly, we can represent minus 3 by 2 and 3 by 2 on the number line. So 3 by 2 is 1, 1 by 2, and that is 1, 1 plus 1 by 2. So 3 by 2 lies between 1 and 2. So we will divide the line segment between 1 and 2 into two equal parts and call it point Q. So this point Q represents the rational number 3 by 2. And the rational number minus 3 by 2 is to the left of the 0, and it lies between minus 1 and minus 2. We then again divide the line segment between minus 2 and minus 1 by minus 2 and minus 1 into two equal parts, and that point is called Q dash. And that's how we represent 3 by 2 and minus 3 by 2. Similarly, we can also mark points like 5 by 2, minus 5 by 2, 7 by 2, minus 7 by 2, and so on. So now that we know how to represent rational numbers on a number line, we need to understand how to compare those together. So there are multiple rules in order to compare two rational numbers. Let's have a look at it. So the first one is that every positive rational number is greater than 0 and every negative rational number is less than 0. Second, every positive rational number is greater than every negative rational number. Next, for comparing any two positive rational numbers, we compare them as fractions. So in order to do that, we can first convert them into like fractions, and then the fraction with the greater numerator is greater. But things do change when we try to compare two negative rational numbers. This takes a couple of steps. First, we convert them into rational numbers with positive denominator if it needs to be. Then we find the LCM of the denominator. We convert each rational number obtained previously with the LCM as their denominator. And then the number with the greater numerator is greater. We will understand this more clearly through the examples I will go through later on in the chapter. Once we understand how we can compare two rational numbers, we need to work on how to insert rational numbers between any two rational numbers. First one is to find the mean of those two numbers. So in order to insert a rational number between minus 2 by 5 and 3 by 4, we find the mean of minus 2 by 5 and 3 by 4, which comes out to be 7 by 40. Hence, 7 by 40 is a number which lies between these two numbers. In the next method, we find the LCM of the two denominators and then change the given rational numbers to equivalent rational numbers with the LCM as their common denominator. And if it is necessary, we can multiply the numerator and denominator by n plus 1, where n is the number of rational numbers we need to insert between the two values. Let's understand this better by looking at this example of inserting 6 rational numbers between minus 3 by 2 and 5 by 3. So following the method above, we will first take the LCM of the denominators 2 and 3, which is 6, and then convert them into like fractions, the whole fraction. And this comes out to be minus 9 by 6 and 10 by 6. And then we will find the integers between minus 9 and 10, which can be minus 8, minus 7, minus 6, all the way up to 7, 8, 9. And thus we can insert the rational numbers between these two values as minus 8 by 6, minus 7 by 6, minus 6 by 6, all the way up to 7 by 6, 8 by 6, and 9 by 6. I hope you liked the video. Please don't forget to like, share, and subscribe for more content like this. Thank you.